The scalar product of two vectors is also known as the dot product. And what is it? It's A times B, vector A times vector B, is equal to the magnitude of A times the magnitude of B times cosine theta. Well, we know we can find magnitude of A and magnitude of B by using the Pythagorean theorem. We know what cosine is. What is theta? Theta is defined as the angle between the two vectors when joined tail to tail. I have vector A and vector B joined tail to tail. There's theta between them. Also, the angle theta can be obtuse. Here's vector A going that direction, vector B going that direction. They're joined tail to tail. You need to know this. A times B, the dot product of A, vector A times vector B, is magnitude of A times magnitude of B times the cosine of the angle between them. Now, if you're asked to find the dot product of A dot B, you know it's magnitude of A times magnitude of B times cosine of the angle between them, theta. Well, if here is A, vector A, and here is vector B, there is theta, the angle between them, we could make this into a triangle and calculate this the long way. We know that A, if this is in 3 dimensions, is going to be x squared plus y squared plus z squared square root for my A values of x and y and z, and B squared will be x squared plus y squared plus z squared square root for the values of vector B. We could then find this distance c using the points here and using the distance formula, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, and find this distance c. Once we find that distance c, we could use the cosine rule, and it says c squared here, which we would know from the distance formula, is equal to a squared plus b squared minus 2ab cosine theta. Well, the c, angle c, if we put an angle c there, that would be the same as theta, and we could solve for theta and then plug in, plug in, plug in. That would be the extremely long way. We have, fortunately, another way. It's easier to do. Instead of finding the scalar product or dot product by using the distance formula and finding the magnitude of A and B with the Pythagorean theorem and then using the cosine rule, we can simply state that A is made up of these components, which translates into these components, and B, the vector B, is made up of these components, which translates into these components. Well, if that's the case, then the scalar product of the dot product is simply x1 times x2 plus y1 times y2 plus z1 times z2. This is extremely important. This is what you're going to need to use to find the scalar product between two vectors. The scalar product or dot product of vectors in 2 dimensions is even easier. A is now just defined as x1, y1, which translates to x1i plus y1j, and B is x2, y2, which is x2i plus y2j, and our dot product simply becomes x1 times x2 plus y1 times y2 in 2 dimensions. When do we use this scalar or dot product? Well, it is most useful for calculating the angle between two vectors that are put together tail to tail. If A dot B is equal to the magnitude of A times the magnitude of B times cosine of the angle between them, then we can divide both sides by the magnitude of A times the magnitude of B, and therefore our conclusion would be that our theta is equal to inverse cosine of A times B divided by the magnitude of A times the magnitude of B. And we're going to take that whole thing to the inverse cosine. We have 3 special cases of the scalar or dot product. First of all, what if the two vectors are perpendicular to each other? For example, if here is vector A and here is vector B, and between them we have a 90-degree angle. Well, then they are perpendicular, and then the dot product becomes A times B, or A dot B equals magnitude of A times magnitude of B times cosine theta, and the theta is 90 degrees. We know from our work with trigonometry that at 90 degrees our x component is 0. So cosine 90 is 0, and so the magnitude of A times the magnitude of B times 0 is 0. This is the most important thing to remember. For perpendicular vectors, the dot product is 0. Our second special case of a scalar product is the 0 vector. For any vector A times a 0 vector would give you magnitude of A times the magnitude of 0 times cosine theta, which is also equal to 0. We saw that with perpendicular vectors as well. We can conclude from our first 2 special cases of the scalar product that if the dot product A times B is equal to 0, then A and or B are the 0 vector, or that A and B, the two vectors, are perpendicular, with neither one of them being the 0 vector. Key point, A dot B equals 0 means you either have a 0 vector or, more likely, in our case, that they are perpendicular vectors. The angle between A and B is 90 degrees. Our third special case of scalar products are parallel vectors. Well, if I have two parallel lines here, then the theta between them, if I add them up or if I join them tail to tail, the angle between them is 0 degrees. And we know cosine 0 is 1. Here is cosine 0. Remember, cosine is their x component, and that will be 1 here. So if I put a 1 in for cosine 0 becomes 1, then A dot B becomes the magnitude of A times the magnitude of B. What if they're anti-parallel, meaning A is going this way and vector B is going that way? Well, if I put them tail to tail, I'd have a straight line, and the angle between them would be 180. What is cosine of 180? Well, here is pi, or 180. Our x component is -1. So I'd just substitute a -1 in for cosine 180, and I'd get A dot B, or the dot product, or the scalar product, is equal to negative the opposite of the magnitude of A times the magnitude of B. And of course, I find these magnitudes by using the Pythagorean theorem.